Hello, teacher.
Hello guys, how are you doing?
Hello.
Nice to see you.
How are you, Mr. Bruce?
Yeah, I'm fine, thank you. Quite unexpected weather, I would say. I heard that it's supposed to be already snow and frost in the middle of October, but apparently not for this year. But I don't believe that it will last for very long.
Are you in Astana?
Yes. Yeah, I'm on campus now. Campus is quite empty and unusual for a university to be without students. Also, not all faculty members are around, so really not many people.
I heard that in Nazarbayev University, gym is already open.
Yeah, it is open. Usually there is a requirement either if you go to gym or to labs, you need to do every 2 weeks PCR test for COVID. Then with this negative PCR test, you are allowed to go there.
For students, is it open?
Good question. I think that it should be open for those who are allowed to be on campus. But if you have negative PCR test within the last 2 weeks, maybe it's also allowed to students come like from outside the campus. That I don't know, but you can contact some sports center or some university administration for that and figure it out.
Okay, thank you.
But I believe without negative PCR test, no one will be allowed to go to any buildings of the university. Okay, so more people have joined. Before we continue our discussion of Kepler's laws, I just wanted to remind you, and maybe if you're in contact with your friends who also attend this course, I would like to remind that on this Saturday, we will have midterm 2, and there will be included problems from our previous topic, which is like torque, angular momentum, and since it was the last topic and you didn't have so much time as for previous topics, just wanted to remind you that you practice in solving some problems in both torque and angular momentum, like also some rolling of objects on inclined plane. All of these kind of problems will be in the together with other topics, but also will be in the midterm, and also practice a bit with this cross product of vectors, like vector product, because if it's necessary to find torque, you need to do some vector product of radius vector and force. So just be aware of this, and it's a matter of just few times practice, so you have some confidence in what you're doing. Because you didn't have much time for this last topic, and it's kind of not so simple topic. Better keep this in mind before Saturday and do some practice.
Mr. Bruce, how many questions will be in midterm? And how many time?
I cannot say exact number. I don't know, but most likely it will be something like 7. Again, plus minus 1, but around 7. It will be similar. Last time, how many problems did you get? It was 8.
Yes, 8.
Oh, okay. So I guess it will not be much different, but probably something like 7.
8 problems for 1 hour, yes? Approximately.
Yeah, approximately. Maybe 8, 7 problems for 1 hour. Yeah, last time you did, in general, like average scores were quite reasonable, and you did quite a good job. So just keep going, practicing more, and specifically pay attention to this like last topic, since you didn't have enough time. But well, there was this 1 week of break, which can be used in different ways. So you can practice solving problems, or you can just go and relax somewhere. So just be aware that it's coming, and this topic will be also included. So practice in some vector products and torque and angular momentum, kinetic energy of rotational motion of rigid bodies and stuff like that.
So this week topics will not be.
This week topics will not be included there. It will be for next midterm, like one after second midterm. Okay, guys. So now I think everyone already joined who wanted, and we can continue. So we stopped at the third Kepler's law. So we defined all Kepler's laws. I would like to highlight this fact again, because we will discuss it later, that Kepler's laws, they are purely empirical from experimental astronomical observation. So the just observation of bare eye of moving planets with respect to stars generated this amount of data, which was analyzed by Kepler and summarized in his 3 laws. And that was done before Newton came with his general universal gravity theory. So actually it was based on this, and the ideas how it was related, the general, the universal gravitation law, how it was linked to Kepler's laws, we will consider also in this discussion. However, now we need to finish with the third law of motion, and as you remember, we defined it as, well, in short, it is the square of period of rotation of the planet about the sun is proportional to the third power, proportional to this radius. Sorry, more general case, it's not radius. It's semi major radius, which is A in third power. So semi-major radius is of an ellipse is this distance from the center of the ellipse to this furthest point of ellipse. So this is A. And a particular case of ellipse when semi-major and semi-minor radiuses are equal is a circle when we just have radius. So in considering from the quantitative point of view, third law of Kepler's law, we will consider for simplicity the circular motion. First of all, it's also in some extent elliptic orbit, but just in specific case, ellipse can be represented as a circle with this ellipticity coefficient E equal to 0. So it's just a circle. When two focuses of ellipse, F1 and F2, are located in the center of the circle. So let us then write, let's consider sun with mass M capital S. Then we have some planet which moves, like rotates about the sun in circular orbit. That is actually very close to true because most of actually all planets in solar system, officially planets, except Pluto, which is not considered anymore as a planet, they have very close to circular orbits. So their ellipticity of their orbits is very small. So this assumption is quite close to real conditions. And this orbit has some radius. So this is our planet with some mass, and it has some linear velocity. So according to the second Kepler's law, which states that the radius vector of the planet sweeps out equal areas per unit time, means, and we discussed this last time, during the last discussion, it means that for the circular trajectory, circular orbit, it means that the angular velocity and also linear velocity of the planet is constant. So since we don't change the radius, the distance from the sun to the planet, it means that the angular velocity and linear velocity should also not change, because as we discussed last time, in the case of in the case of the ellipse as an orbit, elliptic orbit, we increase linear velocity when radius vector decreases, and in the contrary, we decrease linear velocity when radius vector increases. So the further the planet is from the sun, the smaller linear velocity. In case of a circular orbit, radius doesn't change and velocity also doesn't change. So these parameters are constant. So based on that and taking into account circular orbit, we can write that gravity force, actually here, Fg, should be equal to, according to the second law of motion, to the mass of the planet times centripetal acceleration. And from this equation, we can write for the gravity force, we use the universal gravity law. So we have gravitational constant, mass of the sun times mass of the planet divided by r squared is equal to, sorry, it's not capital M, to mass of the planet times, we need to express this radial acceleration, and this is equal to v squared divided by r. So we can write here v squared divided by r. So from here, we also can express v linear velocity as the length of the this circle, 2pr, divided by time it takes for the planet to make one revolution about the sun. So it's this period, t. So now we can substitute expression for v in this equation. And what do we get? This will be g m mass of the sun divided by r squared. Here actually we can cancel out mass of the planet. We don't need to write it anymore. Is equal to 2.
Mr. Bruce,
Yes.
sorry for disturbing, but what about
No.
radius?
Can you repeat? What about what?
What about radius? Can we cancel one radius from the left side and one radius from the right side?
Yeah, you're right. We can, yeah, we can do it definitely. Yeah, I didn't. So then we delete here. Like this. Okay, good, thank you. Then we have 2 pi r divided by t, and this is square because we have v squared. So from here, what do we get from here? We can put this t squared to the left. T squared is equal to 4 pi squared. Then we have r squared in the right, and we have 1 r in the left. So we have actually r cube. And this is divided by g m mass of times mass of the sun. So this is this can be represented in terms of a constant Ks, some constant which describes our sun, times r cube. So we see that we actually came to this statement of third Kepler's law with this equation, because This can be written as t squared proportional to r cube. So which is actually the statement of the third Kepler's law. In this case, we use r, which is the radius of circular motion, but it is just one special case of elliptic orbit and can be also applied to any orbit with any shape. So this Ks is some constant. It's 4 pi squared divided by gravitational constant and mass of the sun. It will, of course, change for different objects. So we can calculate this constant also for Earth when we consider motion of our satellite moon about us. But in any way, we can apply this to any objects. In this particular example, we considered our sun and some planet moving about it. Let us maybe just consider some option of application of this third law of Kepler's law, which is quite convenient for different research applications. And we will talk a bit about this later. So what if we want, let's assume that we don't know the mass of the star. So we observe some star. We don't know its mass, but we see some exoplanet rotating about this star with certain period, time period, which we can measure. So we know that according to third law of Kepler's law, the square of the period is equal to 4 pi divided by general like the gravity constant, mass of the star, times radius in the third power. Okay, so we don't know the mass, but we can measure the radius, the distance of this planet from the star, and we can also measure the period. So from this, if we measure these two parameters, we can easily determine mass of the star. So it's 4 pi r cube g divided by t squared. And it actually very simple approach to get the unknown mass of the object about which some planets or some other objects are rotating. And nevertheless, that it looks so trivial and simple, this year Nobel Prize was literally given to people who were employing this concept in their research. So this year, half of Nobel Prize was awarded to Reinhard Genzel, and from he's director of Interstellar Max Planck Institute, and Andreas Gass. She is professor at University of California, Berkeley. So what they did, they actually were observing stars which are very close to the center of our galaxy. They were calculating the orbits, like distance from the center to the planets, and their periods of rotations about the center of the galaxy. And by assuming that we have not a star, but some black hole in the center of the galaxy, by applying third Kepler's law, they were able to calculate the mass of the unknown and invisible huge black hole in the center of our galaxy. So the approach, of course, they did also in addition, like many other investigations, but this is the main concept of applying very simple Kepler's law, which comes from the dawn of history, from 1600 Middle Ages actually, and was received by empirical observations with naked eye. So in their case, the main technological step which have been done by these people, they managed to develop such techniques which allowed them to observe not just planets moving around the sun, but stars moving around the center of our galaxy, which is a big technological challenge. However, once you manage to see these stars moving around the center of the galaxy, you apply this simple concept and answer a very fundamental question of revealing the secrets of the structure of our galaxy, Milky Way, and giving the exact number, the determined value of the mass of the supermassive black hole in our galaxy. So that, I believe, quite interesting example how very old, established, and trivial concepts from basic general physics can be applied nowadays to do groundbreaking achievements in modern science. And yeah, this year their work has been recognized by the most prestigious prize in science, which is Nobel Prize. Okay, so we have finished with discussing the all three Kepler's laws. I mean, not only giving their definition, but also step by step considered all physics behind these laws. And now I would like to spend some time coming a bit backwards to the universal gravity law. So we wrote at the beginning of the last discussion that gravity interaction between two bodies is equal to some constant, gravity constant, times, let's again consider sun and planet. So mass of the sun and mass of the planet, and it is reversely proportional to the square of distance between them. So this, as I mentioned before, was derived by Newton. And the question is, how did he come to this point? He couldn't just see it in his dream. So there should be some basement for that. The basement for that were empirical Kepler's laws, three Kepler's laws, which we considered before. So let us just go through this way of coming to this point when you can derive universal gravity law from Kepler's laws. So again, we will consider only a circular orbit for simplicity. And we can write that based on the, in case of the circular orbit, the gravitational force should be compensated by the centrifugal force for the planet in order to keep it in the stable orbit. So the centripetal acceleration we need to deal with AC is equal to V squared divided by R, the radius, the distance between the planet and the sun. So we already wrote that V, the linear velocity, is 2 pi r divided by t. So the acceleration will be 4 pi square r divided by t. So we have r square here, so we use v square, and we have one r in the denominator. So that's why we end up with this expression for our acceleration. And from the other side, we can write, according to the second law of motion, that this is equal
Excuse me, Professor.
Yes?
Isn't it t squared?
Yeah, t squared. Sure. Thank you. I missed it. Yeah, we have v squared, and that's why we have t squared. I was looking only on r. We also can write that the gravity force divided, this is equal to the gravity force divided by the mass of the planet. This is also will be our radial acceleration in order to compensate each other. And now let us do the following. Let us consider this equation and multiply it by r squared, left and right side. So we do it in order to come to the equation which describes third Kepler's law. So as a result, we will get 4 pi square r square divided, not square, but r cube, divided by t square. This is equal to F gravity r square divided by mass of the planet. So pi is the constant, and this ratio is also constant, because we know from the third Kepler's law, t square is equal to some constant times r cubed. So the ratio r cubed divided by t squared is some constant. So in the left side, we have some constant. If the left side is a constant, then the right side is also a constant. So this is a constant. And that it means that gravity force is proportional to mass of the planet divided by r squared. Or we can write that F gravity to be kind of more precise will be equal to some constant times mass of the planet divided by r squared. So mass of the planet and mass of the sun, I mean, there is not fundamental difference between these masses. They act and interact between each other equally. There's no difference between them. And that's why if this gravitational force proportional to the mass of the planet, it should be also proportional to the mass of the sun. So that's why in this constant we have hidden mass of the sun. So we should write constant, some constant prime, which should be different, equal to mass of the sun times mass of the planet divided by r squared. And this is already our universal gravity law. So where constant prime is equal to the gravity constant. And this value of the gravity constant was calculated experimentally by scientist Henry Cavendish in 1798. And actually there is nowadays Cavendish lab in Cambridge University. So it's actually physics department at Cambridge University. So in name of this scientist was established this Cavendish lab, and very many prominent scientists and Nobel laureates were working there as Cavendish professors. There's a position, Cavendish professor at Cavendish lab. And in particular, Rutherford, who found the structure of the atoms, Mott, who did great contribution to understanding of charge transfer in amorphous solids. And nowadays, like Cavendish professor is Sir Richard Friend. He is working on organic electronics. Actually, it's my field of research, and that's why we're just aware of him. Our group collaborated. So these historical moments are still there, and such contributions which was made in like 1798 is still well remembered and respected nowadays. So those who are physicists and have a chance in future to do some research stay or maybe PhD at Cavendish lab, that would be really great. You will be just in touch with the history of physics, literally. So as you see, with such simple steps from the involving second and third laws of Kepler's laws, you can come to formulation within some constant formulation of the universal gravity law. And the constant, of course, itself should be calculated based on some experiments. So actually, Cavendish did experiments with two masses hanging on the some rope. So equal masses m, next to some big masses like capital, also equal capital M. And was attached a mirror to this rope, and some light beam was directed on this mirror. So when you place these masses close to big mobile masses to big immobile masses, there is some force, like interaction between them. It's very tiny, but enough to tilt a little bit, like rotate a little bit this row. And since you can place some screen quite far away from this experimental setup, you can see deflection of this reflected beam, even if there is very small rotation. And by measuring this, Cavendish managed to calculate the gravitational constant. Okay, so now I think it's time for us to go further and consider gravitational field. So one of the problem Newton experienced during presenting this universal gravity law, people were not convinced how is it possible that bodies which are not in contact with each other can interact with each other. Kind of counterintuitive. From everyday life, we see that in order to have some impact on another bodies, you need to have a physical contact. However, like at that time, Newton couldn't answer this question and remained a mystery. You just see that it is indeed like this, it works. It is based on real experimental observations. However, you don't understand the reason, the mechanism, how two bodies can interact with each other without direct contact. So later, this was explained in terms of the proposed gravitational field. So actually, a gravitational field is the ratio. So we can claim that in certain point of space, there is some gravitational field with strengths of G equal to the ratio of the gravitational force which is exerted to the body in this location of the space divided by its mass. So it's actually mg is this product is the weight of bodies, which we are familiar with and used quite a lot previously. So you can call acceleration of free fall as a strength of gravitational field. And if we consider now equation for the gravitational force, strength of the gravitational field will be equal to minus G m Earth. Let's consider example on Earth's surface divided by r square times unit vector of radius vector. So this minus, so it's in vector form. This minus means that gravitational field is directed towards the center of the Earth. So we know from before, when we considered potential energy, that potential energy of some body which is on some height or above Earth's surface can be calculated as like U equal mgh. So this is true when we assume that G is a constant. And this is also true when we remain quite close to the Earth's surface. However, we showed it on the previous discussion that gravitational force decreases and this acceleration of free falling also decreases once we go away from the Earth's surface. And we would like to have more general, derive now more general equation for the potential energy of gravitational field, which takes this into account. So we will not only use this equation when we consider J as acceleration of free fall as constant, but we will take into account the fact that it is G is a function of r distance. In this case, actually, it's distance from the center of the Earth. So for this purpose, first we need to recall what is by definition potential energy in general. So change in potential energy is equal to the difference of final potential energy and initial potential energy. And this is equal to negative work, which is done by potential force when we move our object in gravitational field from initial to final position. And I guess today we are running already out of time, and it would be better that we don't interrupt the derivation of this equation. So we will start our discussion on Friday with this definition, general definition of the potential energy, and proceed further in order to have it solid in one piece, so you don't have options to be confused with this. Okay, do you have any questions regarding the current material? So just recall what we have done so far. We finished, we introduced last time the universal gravity law, then defined 3 empirical Kepler's laws, discussed all physics behind these laws, why they are defined this way or and not in another way. Based on the Kepler's laws, we have shown that it's possible to, within some constant, to derive universal gravity law. And now we just started to discuss the gravitational field and like introduce the concept of gravitational field and try to calculate the potential energy in gravitational field for the general case when we take into account the space dependence of strengths of gravitational field, which is space dependence, like location dependence on acceleration of free fall, g. And starting from this equation, which defines in general case the nature of potential energy, we will proceed further during next discussion on Friday. and calculate this equation, derive the equation for the potential energy in gravitational field. Okay, keep in mind that I will remind again you on Friday, if I don't forget, but on Saturday you have midterm 2, so practice problems, and don't forget about this angular momentum and torque concepts, which we discussed just before the fall break. Okay, then thank you very much for attention. Yeah, have a,
Excuse me, Professor,
yeah, sure.
can I ask one question regarding the theoretical part of derivation of third law of Kepler?
Yeah, sure.
So we already proved the third law with by using university gravity law, but actually, as I know, university gravity law was defined after the Kepler by Newton.
Yeah, you are right. So
How did Kepler came up with a solution?
yeah, so we did it because we tried to understand what is physics, what physics is behind this third Kepler's law. That is totally, absolutely true. And this is, of course, based on the universal gravity law. However, Kepler, he didn't ask a question to himself, what is behind this law? He just formulated his 3 laws based on what Tycho Brahe, his teacher, and he observed with their naked eye during these astronomical observations. So he found that period squared second power of period is proportional to the radius of the orbit in the third power. So that is it. He didn't have the explanation of this. So it's just based on this experimental data analyzed for different planets, measured in different time. He came up that this is always true. Doesn't matter which planet you take, always the period square of the period is proportional to the radius of this orbit in third power. That's all. But later, when Newton considered 3 Kepler's laws and laws of motion, he could go further and derive the gravitational universal gravity law. And now, of course, when we can go backwards and explain each of Kepler's law in the light of universal gravity law. But initially, it was just statement based on experimental data and nothing else. It was not explained in any way.
Okay, thank you.
Mm-hmm. Yeah, so it was just experimental observation and summarized summary of their experiments. Other from that, Kepler didn't have any explanations of these dependencies. That's why it's called empirical result. When you describe some empirical equation or formula, means that you can describe experimentally observed law in terms of some mathematical equation, but you cannot analytically derive this equation. It just describes what you see, it works, but you don't have a theory which explains this. That's why in this case, equations are called empirical, or some statements are called empirical. It doesn't mean that they are not true. They are true because they are based on real experiments, but they don't have theory behind them. And only later theory comes up, and these equations can be analytically derived. Okay, thank you for question, and hope to see you guys on Friday. Have a good evening and take care. Bye bye.
Thank you. Goodbye.
Bye.